Alright, so the next part, now that you've learned about a few of the special functions like how to take the derivative of a logarithm and a sine and a cosine function, the next part is an absolutely essential part of calculus, which is called the chain rule. Now this video is just a brief, very theoretical introduction to the chain rule. And in order to understand the chain rule, you have to start with what exactly is a derivative. If you have a function on an xy plane, like this gray line, this gray curve that I've drawn here, the derivative is the slope of, if we're looking at this point here, the derivative is the slope of a tangent that passes through that point. Now, if we zoom in on the function around this point, so imagine that what I'm doing now is looking at that little part of the gray function in a magnifying glass, what I'd really see is a very gradual change in the inclination of that function. And so one way to think about a tangent is that you're taking this really tiny little bit of run, call it dx, and this really tiny bit of rise, call it dy, and you're just extending that dx and that dy, that slope, outwards in either direction in order to form a tangent. Okay? So that's why the most accurate way to write the derivative is to say dy over dx. Because the derivative really is the slope of the tangent, which really is the rise, namely dy, divided by the run, which is dx. So when we say dy over dx, we really mean a division problem. dy divided by dx. The only problem is that both dy and dx are infinitely small. So this is actually this is the result of a limit, which is why we spend so much time on limits during day one. Now, the fact that this is a division problem, or at least you can think of it as a division problem, means that you can do a lot of the arithmetic that surrounds division problems. So, for example, if you had 12 times a infinitely small piece of y is equal to 16 times an infinitely small piece of x, then you could rearrange this formula to say that dy over dx is equal to 16 divided by 12, which is the same thing as, what was that, 4/3? Okay, so one thing you can do is you can treat dy and dx like any other variable and multiply them and divide them, and when you divide dy by dx, you have a derivative. In other words, what this formula now says is that the derivative of whatever function we're talking about is 4/3. This is getting a little ahead of ourselves into the field of integration and, to a lesser extent, differential equations. But getting back to the chain rule, since this is a division problem, we can say the derivative of the derivative of f I'm having trouble drawing my O's there. Derivative of f is the same thing as df dx. Now, what if we introduce another variable, call it g? So if we have df dx, and if we can take differential slices, infinitely small slices of f, and infinitely small slices, otherwise known as differential slices of d, well then we can also take infinitely small slices of g. So if we multiply this by dg over dg, we're really not changing the value, right? Anything divided by itself is 1. So really all we're doing is multiplying by 1. Multiplying by 1 doesn't change the value. And then multiplication is cumulative. So, I'm sorry, not cumulative, commutative, so you can switch around the orders. So this is going to be, if we change this around to df over dg times dg over dx, we have ourselves the chain rule, which, cutting out the middle part, the chain rule says that df, let me give myself a little more space, df over dx is going to equal df dg times dg dx. Okay. This might not seem like a particularly useful outcome, but it is actually critically useful for solving any calculus problem of even intermediate level of complexity. Now, I'm going to pause for a moment and go off topic a little bit. If you have a background in multivariable calculus, which if you're taking this class, I really doubt you do, but you never know on the internet who's going to see your videos. So I know that in multivariable calculus, the chain rule is more complex than this, and this line of reasoning starts to break down in a multivariable system. But remember, my goal is to teach just enough calculus so that high school students can take the AP Physics exam. So within the scope of my class, this works just fine. However, if, as a student, speaking to my students now, if you go on to a career in engineering, you should take a very useful class called multivariable calculus, in which case you'll have a much more complicated definition of the chain rule. So don't hold this too dearly. All right, so if the chain rule tells us that df dx is going to be df dg times dg dx, this is kind of useful because it allows us to take a complicated function and break it into two relatively simpler functions from which we can take the derivative. So really, this is useful when you have a compound function. In other words, when you have a function, an outer function, f, which acts on an inner function, g, which acts on your independent variable, x. Okay? So, in general, you use the chain rule when you have a compound function. A function inside of a function. One of my students called this funcception after the movie Inception. It's a dream within a dream. Chain rule applies to functions within a function. Yes, this is a stupid joke. All right, so how do you know you got a compound function? Well, a dead giveaway for a compound function is parentheses or brackets okay, or absolute values absolute value bars or anything like a parentheses. If you have complicated stuff inside of a square root, that's another function inside of a function situation. If you have complicated stuff, a sine, cosine, or exponent, sine, cosine, not exponent, log, natural log. If you have sine, cosine, or natural log acting on more than just your independent variable, more than just x. So for our identities alone, we can get by on saying that d dx of ln x. Okay, that just takes an identity, and you can say it's 1 over x. But you use the chain rule to say if you have a function like d dx of the natural log of x cubed minus 6. Okay, because here the x cubed minus 6 is your inner function, your g of x, and then the natural log part is going to be your f of x. Okay, so first step is to know when to use the chain rule, and like I said, key term is compound functions, or use it on a compound function. All right. The next step is how to use the chain rule. Once you realize that you know you have to use the chain rule, then let's go about figuring out how to use it. You use the chain rule by following a series of steps. Really, it's pretty generic. Step 1 is to identify your inner function. Okay? And the flip side of that is to identify your outer function. Actually, wait, let me call your inner function. That's going to be called g of x, or g of whatever your independent variable is. If your independent variable is t, then it's going to be g of t. Next step is to identify the outer function, but not in terms of your inner, your independent variable. You define your outer function in terms of your inner function. So you call it f of g, not f of x. So this has to be in terms of g, not x. All right, let me, as I show you these steps, let me work through an example. In fact, let's just use the example from the last problem, natural log of x cubed minus 6. Okay, so if we have h of x equals natural log of, when I write too close to the top, things get a little messed up. Alright, so let's say we got h of x equals natural log of x cubed, what was that, x cubed minus 6. Okay, identify the inner function. So in this case our g of x is going to be x cubed minus 6. It's the stuff inside the parentheses. Okay, and our outer function is going to be f of g, and that's going to be the natural log of g. So that if you were to substitute the inner function into the outer function, in other words, if you were to take out the g and use this the top expression for g, then you would be back where you started. But the point is not to get back where we started. The point is to do some calculus. So those are the first two steps. And if you don't get those two steps right, oftentimes you'll end up with a problem that's impossible to solve. So dividing these up properly is a pretty key skill. Okay? Step 3, find dg dx. Okay? In other words, take the derivative of g with respect to x. Alright, so if g of x is 3x x cubed minus 6, then dg dx is going to be d dx of the quantity x cubed minus 6. Alright, this is a straightforward power rule application, so d dx of 3x, dg dx is going to be 3x squared. Alright. Step 4. Find df dg. Okay. And as a follow-up to this, you have to, after you're done with the calculus part, you need to substitute g of x back into the equation. Back into whatever you found into df dg. Now, it's important to realize in this step that we're taking the derivative of f with respect to g. So we are considering that inner function to be an independent variable for this step. It's not our independent variable, but for this step we're treating it that way. Okay? So we say that wrong color. df dg is going to be d dg, the derivative with respect to g, of our outer function. So that's going to be the natural log of g. Well, if you remember, the derivative of the natural log of x is just 1 over x. So if we change all the x's to g's, we have something that matches this perfectly. Which means that we can just call this df dg is just going to be the same thing as 1 over g. Okay? But we then After we have gotten rid of the DDG part, then we have to do this step, this substitute g of x back into dfdg. So we have to take this term for g in terms of x and drop it into there. Okay? So instead of saying dfdg is 1 over g, we're going to call it 1 over x cubed minus 6. Alright, the last part of using the chain rule is to actually use the chain rule, which is to say that df dx is going to be df dg times dg dx. In other words, you take the result from step 3 and you multiply it by the result from the end of step 4, and then you're done. Maybe you have to do a little bit of algebra, but you're at least done with the calculus part of this. So I'll do step 5, make a little enclave for myself right here. Alright, so d h dx is going to be the same thing as df dg times dg dx. Okay, df dg, that's 1 over x cubed minus 6, and dg dx is 3x squared. And that's really as far as we can go. You can maybe do a little bit of simplification from here, but this is your answer for the derivative of the natural log of the quantity x cubed minus 3. Alright, so that's some basics of when to use, what the chain rule is, when to use it, and how to use it. The next 2 videos are going to be a series of demonstrations of how to use the chain rule.